Our second reaction is significantly less useful, but it's important to know, and the intermediate in it, the benzyne, is relatively useful in a variety of other contexts as well, like Diels-Alder reactions. So this reaction requires much harsher conditions. It will involve a leaving group, but won't have the electron withdrawing group on the ring. So in an example of this benzyne chemistry, which is elimination addition, this is unusual and new, you might have a starting material like this. So no electron withdrawing group, just a leaving group. And then you'll treat this with a nucleophile, like sodium hydroxide, or a sodium amide. That's what that is. Generally in either very, very harsh conditions or at a very, very high temperature, which is why this one is a little bit significantly less useful than the other one. But let's say we're doing it with sodium hydroxide here. We'll probably do it at something like 350 degrees Celsius, so very hot. And we'll achieve substitution. Now, the substitution doesn't have to be at the place where the bromine was, which we'll look at as we look through the mechanism. So here the mechanism is going to start not with the addition, but with the deprotonation. So we're going to deprotonate at one of the positions next to the halide. So here our base and our nucleophile is hydroxide. So we're going to start by deprotonating this. And that's why this needs such a high temperature, because this is not a reaction that would happen under normal circumstances, this deprotonation. And it's what sets everything else off. So now we have a lone pair on this carbon. And what that lone pair will do is eliminate the bromine. So we start with a deprotonation. This is our base, this is our acid, terrible acid, why this needs to be done at such high temperatures. Then we have the elimination of our leaving group. So bromide is kicked off. And now we're left with the benzyne. Called this because it's a benzene with one triple bond. This benzyne now is going to be attacked by a hydroxide. And that hydroxide can attack at either position. So it can either attack at this position or this position. It has to attack at one of the carbons of the benzyne, which is another reason why this reaction is less useful, is because the nucleophile doesn't necessarily end up where the bromine was. So I'm going to show it attacking the top carbon. And now we have a lone pair here. But notice that the benzene remains unchanged. So we lost this triple bond, but we still have the benzene intact. So now we have this aryl anion, which can be protonated by water. We generated water in this first step. So this is now the base, and this is the acid, to give us our final product. And hydroxide. Unfortunately, this phenol and hydroxide react again also to produce water and phenoxide. So this reaction often needs, as a second step, acid to protonate the phenol. So this acid-base reaction happens. We want to fix it with another acid-base reaction. So that's not something that's intuitive. It doesn't make sense as like an efficient way to do it, but it is the way the molecules react, and there's nothing we can do about it except to add acid. Let's look at another example. Here, I've blocked off this site with a methyl group. We see the leaving group here, And so to deprotonate, we must be deprotonating at this position. So we can figure out that this is a benzyne reaction and not an SNAR because we don't see any nitro groups on the starting material. What that means is that their intermediate here must be something like this. For this CH3 group, we can't have the benzyne there. And we can attack at two different positions. This position here and this position here. So we're going to get two different products. One where the amino group is here, and one where our amino group is ortho to the methyl. So we have one where it's meta and one where it's ortho. And there's no way to fix that. It's just a result of the intermediate of the reaction.
One thing that often throws students off is knowing which one of these two reactions is happening. So what you want to look for an SNAR reaction are electron withdrawing groups. You see that this reaction has bromine, which is not a very good leaving group for an SNAR reaction, and it has an electron donating group. So it's extremely unlikely to happen through an SNAR reaction. The reagents used are also different, but in a synthetic setting, if you're doing a multi-step synthesis, you may not have those available. So that's sort of how you want to think about which one's happening. Look for electron withdrawing groups. Look a little bit at the leaving group because the fluorine is usually associated with an SNAR reaction.